channel analysis actually does break security. There are very few countermeasures, especially microcontrollers leak enormously. That's why 10 years ago all the smart cards were broken with side channel, without exception. Also, all the cards of 5 years ago we break today, and that's a progression of the technology. So for embedded, you can trust that you can break crypto with it. However, like I've shown, you need a certain level of control that might not be so easy. There's a high noise level in the more complex CPUs that you need to overcome, and that increases the effort. And the question is it sufficient to overcome it, or do you need to add more countermeasures? What are countermeasures? Basically, we distinguish two types: hardware countermeasures, software. Hardware are all kinds of die design techniques, specific circuitry to make power consumption equal, stuff like that. In software, you can do all kinds of randomizations, you can change your algorithm, you can change your protocol to kind of improve your design against these techniques. If you have a key that's only used for 1,000 times and then it changes the key using a sequence algorithm, then you only get 1,000 measurements with one key, and then your side channel attack that works at 50,000 doesn't work anymore. So there are all kinds of ideas in the design that you can use to improve a product without actually changing the hardware yet. When talking about countermeasures, and this is especially for people building things and designing things, it's good to know that there's a company out there called Cryptographic Research, founded by Paul Kocher, who kind of invented this whole class of techniques. And they have a wide range of patents, and they license the countermeasures, especially to all the chip manufacturers currently. But if you need countermeasures, you always need to consider that licensing may apply, depending on what component you use, etc. But also for knowledge on countermeasures, they are the ones that come up with all those new protocol ideas to strengthen your design. And they're in San Francisco, by the way. So, and then kind of taking everything now together, I try to make this table to kind of see how I would rate the difficulty of an attack on a certain kind of system. And this is by no means the truth or the holy grail. I put a special note there that it still happens that on a very complex CPU with a very bad RSA, we break it within a week. But still, for a rough idea, it gives you a feeling for the effort that you require. And that goes, of course, from a basic microcontroller, which is in fact more like a smart card, but without countermeasures, it's fairly trivial. So 1-2 week effort, and that's including figuring out the whole attack, is sufficient. That means that afterwards you can do the attack in a few hours most of the time, because when you know what to do, it's just measuring and doing the attack. And then you see that adding countermeasures and also moving to the more complex CPUs, it adds in the complexity of your tools that you need to use to do the analysis, and it adds in the setup time that you need to actually get the side channel going. So what do we see in the developments? Increasing high-speed acquisition, so like the oscilloscopes, they keep in, the CPUs go up, but the oscilloscopes go just as fast. It becomes more mainstream. There are a few sites. There's OpenSCA on SourceForge, which is a set of MATLAB scripts by an academic, Oswald, that distributed this on the internet. There's the DPAcontest.org, which is a contest to crack a set of files that they put up there and see who gets it the fastest. So there's a lot of interest now in the more mainstream world, as it were. Processor-based, what we see is much more features and countermeasures in chips. So not so much countermeasures against side channel, but a lot of features in secure storage, secure boot, things that make it like removal of JTAG, fusing of JTAG, password protection of JTAG, so you don't get that easy access anymore, and it's not just about reversing the firmware and then you get the keys. Okay, then, well, let's hope this is going to work. Final demo, and this is an SPA attack on RSA. And sorry? Yeah, I was just going to explain. This is a picture to explain this. SPA is simple power analysis. So that means that you only need one measurement or a few to actually do the attack. And you don't need a statistical attack on multiple measurements. And what you see here is a measurement of an RSA operation on a contactless smart card. And the way it works is that you can implement RSA in various ways. And the simple way is to do a square operation for a 0 bit and a square multiply operation for a 1 bit. And that already tells you if I can distinguish a square and a multiply, I can break RSA. So if you use the naive bitwise implementation of RSA, you'll get something like this. And in this case, it's the width. So you see that there's a slight timing variation between this square and this multiply, and this square and this square and the multiply, and that means that you can read off the bits. So a similar kind of demo is now set up here. And again, if it works, what I'll do first is I'll move the probe to a better position. And the idea is that when we measure, you get something like this. So it looks kind of raw. I have to move the probe a bit. Oh, wrong way. Oh, wrong way. So I'm not completely sure because the XY scan didn't work if this is the correct position, but I'm just going to try, see what comes out. So what we're going to do is just take about 10 measurements, this time at 250 megasample, so that's like about 5 times faster than the CPU frequency. But actually for RSA, that's not so relevant. And then we just run it. And actually, I think we can also hear it. Do you hear something here? Okay, so it is a little bit to show that with a fairly simple setup, so this is just a loop antenna, and I think it was also shown yesterday, with a hand scanner, AM demodulation, it's already picking up actually part of that RSA. It's a short RSA, so it's over quite quickly, but the information in the signal is also audible already with AM demodulation. And RSA is quite slow, so probably you can also make a decoder if there's this time variation in the chip. So what the measurement looks like is this. I'll turn this off again. And you don't see that much actually. And maybe if I zoom in, you start to see something, and probably you can already now figure out what's going on. But I can also optimize the signal a bit by just using some filter techniques. I can build a chain, and what I do is I do some steps. I make an absolute of it. That's because it's an EM signal, and the EM is differential, so I make it absolute. I add a resample to compress the data a little bit. And in this case, I'm going to choose a quarter of the CPU frequency. And then I add a low-pass filter to pick out the lower frequency components, which is the RSA bit calculation, which is actually quite slow. I think 10. Let's just try this. See what comes out. Oh, actually, it already looks a bit better. So now you already start to see some variation. And actually, it's a bit difficult to see, but this is actually the first square and a multiply. And a square and a multiply and a square and a multiply and a square and a square and a square and a square and multiply. So actually here we're already again seeing the 1, 1, 1, 0, 0, 0, 1 bits of the RSA in there. And this is not very